Today, we're going to dive into one of the most powerful and honestly most misunderstood ideas in all of science, the butterfly effect. It all starts with this one famous question. It was posed by a meteorologist named Edward Lorenz way back in 1972. I mean, it sounds more like poetry than science, right? But it actually hints at this really profound, almost chaotic truth about how our world works. And you've definitely seen this idea before, probably in a dozen movies or TV shows. You know the drill. Some character goes back in time, steps on a bug, and then comes back to find the future is completely different. It's a fantastic plot device, for sure, but the real story behind it, it's even crazier. Okay, so let's start there. Let's peel back all the layers of the pop culture myth and find out what's really going on with this butterfly in Brazil. Let's get to the heart of it. Because here's the thing. The butterfly effect wasn't dreamed up in some thought experiment about insects. No, it was discovered completely by accident, inside a super primitive computer, and it basically turned our whole understanding of predictability on its head. So let's zoom in on that exact moment of discovery. It's a great story, actually. It involves a pioneering scientist, a computer the size of a room, and a tiny, almost invisible rounding error. So meet our guy, Edward Lorenz, a meteorologist over at MIT. He's using one of those early giant computers to model the Earth's weather. And one day, to save a little bit of time, he decides to restart a simulation from the middle instead of from the very beginning. So to get the simulation going again, he looks at a printout and types one of the numbers back in. But he takes a little shortcut. Instead of typing in the full number, all 6 decimal places, he just rounds it to 3. A tiny, tiny difference. He figured, what's the harm? I mean, it's a change of less than 0.1%. Logically, it should have made almost zero difference to the final result. So he typed it in and went to go grab a cup of coffee. But when he got back, he was completely blown away. The two simulations, they started out almost perfectly in sync. But then, they started to drift apart. And within a couple of simulated months, they were predicting completely different weather patterns. That tiny, insignificant rounding error had snowballed into a massive change. Now, what Lorenz had just stumbled upon, this wasn't just some computer glitch. It was a fundamental property of the universe, a rule that would go on to help launch an entirely new field of science. This is the key takeaway right here. The official scientific name for this is sensitive dependence on initial conditions. All that means is that for really complex systems like weather, even the most microscopic error in your starting measurements makes long-term prediction totally impossible. It comes down to this. The present determines the future, but the approximate present does not approximately determine the future. And check this out. This is the visual heart of the whole discovery. When Lorenz actually mapped out the behavior of his weather model, it traced this incredibly elegant looping pattern. He called it the strange attractor. And as you can see, it just so happens to look, well, a lot like a butterfly's wings. And that beautiful coincidence is how the butterfly effect got its iconic name. So Lorenz's work didn't just explain why weather is so hard to predict. It became a cornerstone for the entire field of chaos theory, which is the study of all kinds of systems that are super complex, dynamic, and, at their core, fundamentally unpredictable. So let's zoom back out for a second, because this isn't just about weather patterns on a computer screen. No way. Once you know what to look for, you start seeing the butterfly effect absolutely everywhere. It's like a world of dominoes. I mean, take ecology, for example. When they reintroduced just a few wolves back into Yellowstone Park, it was a tiny initial change, right? But it set off this amazing chain reaction. It changed how the elk behaved, which let the trees grow back, which then literally changed the physical course of the rivers. Or think about the economy. The 2008 global financial crisis was kicked off by problems in the subprime mortgage market, a pretty small corner of the financial world that ended up toppling the whole thing. It even happens in our digital world. A single post on social media can go viral and ignite a global movement, totally shifting public opinion practically overnight. And of course, on the biggest scale imaginable, this is at the heart of how we understand climate change, where all these small, cumulative changes in what we do are leading to huge, long-term consequences for the entire planet. So this begs a pretty big question. If the world is this chaotic, this sensitive to tiny changes, how do we predict anything? How have we adapted to deal with this fundamental unpredictability? You know, what Lorenz discovered was a massive shift in how we think about the universe. For centuries, since Isaac Newton, the scientific view was that the universe was like this giant perfect clock. If you could just know where all the gears were at one moment, you could predict the future forever. But Lorenz showed us that's not the case. We live in a world where perfect measurement is impossible, which means perfect prediction is also impossible. Okay, so that brings us right back to our original question. If a butterfly flapping its wings could theoretically throw everything off, how on earth do meteorologists tell us if we need to bring an umbrella next Tuesday? Well, it turns out the solution is to actually embrace the chaos. Instead of running just one single forecast and hoping it's right, they use something called ensemble forecasting. They start with the best data they have, but then they create dozens of slightly different starting conditions. They tweak the temperature a tiny bit here, the wind speed a little bit there. Then they run a completely separate simulation for each one, and they look at the whole range of possible futures. It doesn't give them one perfect answer, but it gives them a map of the most likely outcomes. It's brilliant. And this all leads to a really fascinating final thought from Lorenz himself. He pointed out that if a tiny little action can have a huge negative outcome, well, it's just as probable that it could have a huge positive one. A butterfly's wings could just as easily prevent a tornado as cause one. So the ultimate question the butterfly effect really leaves us with is this. If our world is so incredibly sensitive to the smallest little inputs, does that mean that our own small, seemingly insignificant actions have the potential not just to create chaos, but also to nudge the world toward a better, more stable future? Something to think about.